So let's start with question number 31 of friction from H.C. Verma. Just go through the question, all of you. I'll discuss. So this is in many ways the best question of friction in H.C. Verma, and very interesting question because we will involve various different things in this. Okay, you can solve the question by using pseudo force concept. You can solve it by using relative motion concept. You can use number of different things. So let's understand the question first of all. So you have like this plank kind of thing and a smaller block on top of it. So basically in the question, you can ignore the size of the smaller block compared to the length of the plank. Okay? So the plank has mass capital M, the smaller block has mass small m, and we are taking the length of the plank as L, whereas the size of the smaller block is neglected in comparison to that. So you can treat it like a particle. Its dimensions are negligible compared to this. Okay. We also have the coefficient of friction between the road and the bigger block is mu, and between the two blocks is mu by 2. So let's say this one we are writing as mu1, so that is mu by 2, and this one is mu2, that is mu. Now what happens is that initially the system is started towards the right with an initial velocity of v. So at time t equal to 0, the whole system is imparted with a horizontal velocity of v towards the right. Okay? So at t equal to 0, the whole system, that is the block plus the plank, start with velocity v towards the right. So they are imparted an impulse or something like that. As a result of that, at t equal to 0, when the motion starts, what is happening is that this block also has the horizontal velocity v, and this plank also has the horizontal velocity v with respect to the inertial ground frame. With respect to the observer on the ground, both the blocks have this common velocity v. So we have to find the time after which the smaller block separates out of the larger block. Okay. So needless to say, it's a question where the first thing we have to consider is free body diagram and how friction will act on the two blocks. Okay. So we'll make FBDs, okay, and determine the individual accelerations. This is the first method we can do of small m and capital M. Let's start with this. So just make this diagram, I'll show you. Okay, so when I say that, individual accelerations of these two, I will make the FBDs in the ground frame for both of them. Okay, I'll make the FBDs with respect to ground frame. Okay, so this is where it gets very interesting to judge how the friction is acting. Okay, so pay close attention here. So what is happening is that this plank now, it has imparted a velocity towards the right. So on the ground, it's slipping. It's already in the state of slipping at t equal to 0. So immediately kinetic friction has to come into play from the ground. It's got the velocity in this direction, so immediately kinetic friction will start acting on it towards the left from the ground. So this is, let's say, F2. So it is mu2 N2, where we had understood already that this coefficient of friction you're taking as mu. This one is mu by 2. It is the whole thing. Okay. Because it has this velocity. So this is kinetic friction. Okay. And let's also understand the normal reactions. So this one's weight capital Mg, this one's weight small mg, okay, will generate a normal reaction N2 over here and a normal reaction N1 like this between the two of them. Okay. So N1 will be equal to the weight of the smaller block, whereas N2 will become N1 plus this one's weight, so it will become M plus mg. Okay. So N2 is this. Now the thing is that, see, because of this friction, this block is having a tendency to decelerate. So it's immediately having a tendency to decelerate. So in this one's frame, the upper one has a tendency to continue in the straight motion. So the tendency of slipping for the upper one is towards the right. So it will apply a friction on the lower one. In which direction? In this direction. This will be mu1 n1. This is the friction by the upper block. Now, why the upper block is applying the friction in this direction? Because with respect to the upper block, now, this has a tendency of slipping towards the left. Because they were both given the initial velocity. No? So the ground is making this one decelerate. So it has a tendency to slip backwards with respect to this. So this will apply a friction on small m like this. And therefore small m will apply a friction on capital M like this. This is in ground frame. Okay. So क्या हो रहा है ना, ये वाले plank को, the moment the ground is applying the friction over here, why ground is applying the friction? Because it's slipping in the forward direction. So suppose there had been no friction, these two would have continued with the uniform getting behind. So this has a tendency to move forward. So this has a tendency to slip like this, and this has a tendency to slip like this with respect to this. So the direction of frictions are like this. Okay. So in the ground frame, in the inertial frame, this is what the frictional forces look like for both of them. So both of them are decelerated, but at different rates. Okay. So this is also kinetic friction. That one is also kinetic friction. So in the ground frame, the block small m will have the relation that F1 is equal to MA1. Okay. So mu by 2, because mu1 is mu by 2, small mg will be equal to MA1. So this one will have a deceleration of mu by 2g. Okay. Whereas the plank, capital M, it has a net backward force of F2 minus F1 that is providing the deceleration E2. So mu M plus mg minus mu by 2 small mg is going to be equal to capital M E2. So this will give us a value of E2, the deceleration of this one, as mu into 1 minus half, so that will become half. So m by 2m plus 1 into g. Okay. So I've just done some of the steps algebraically. I've just done them mentally, but just subtract these two and divide by capital M, you will understand how we are getting this. So we are getting the individual accelerations, or rather the decelerations of the two blocks. So A1 and A2 are the deceleration in the inertial ground frame. think about it carefully once. It's easy to understand the direction of friction, because I've shown you the direction of slipping of one block with respect to the other, or the block with respect to the plank, how it has a tendency of slipping. Because here they're not starting from rest. Now both of them have the same initial velocity. So the ground is trying to stop the plank. So with respect to the plank, now the block has a tendency to move forward, slip forward. So the friction pair between them will act like this. Okay, so are we clear so far? Diti, you have understood this part? Okay. So now see, once you got the deceleration, if I'm going with this method that I'm solving both in ground frame, so this part of the job is done. Next I have to do what? I have to solve the kinematics. Newton's laws and friction part is done. Next is about kinematics. So what you're seeing now is that this block and this wedge at t equal to 0, they both have the same identical velocity v, but they have different decelerations. A1 like this and A2 like this, where you can see that actually A2 being mu g into 1 plus m by 2m, and A1 being mu by 2g, you can see that A2 is greater than A1. Okay. So now you can convert this to relative motion. Okay. You can convert this to relative motion. So you can see that you use these concepts that velocity of A with respect to B is velocity of A minus velocity of B. Acceleration of A with respect to B is acceleration of A minus acceleration of B. Use these concepts. So next what we'll do is we'll get onto the frame of the plank. So in that frame, what is happening? So the at t equal to 0, the velocity of the block with respect to the plank, that will become how much? 0, because both of them are having the same velocity of the block is vi cap. Velocity of the plank is also vi cap. So relative velocity will be 0. Okay. But acceleration of the block with respect to the plank, now that will become very interesting. Okay, see, acceleration of the block is minus a1 I cap, and acceleration of the plank is minus a2 I cap. So this relative one will actually become a2 minus a1 in the forward direction. It will become like this. Is this minus this now? So it's minus a1 minus of minus a2. So it will become this. So from here you can see that. So I'll just write this like this, that the V relative is 0, but the A relative will become like this, A2 minus A1, which further you can see is mu G, if you take common, 1 plus M by 2M minus half. So that becomes half plus M by 2M. So this calculation. So it becomes mu G by 2 into 1 plus M by M. And this is in this direction. This is in the positive direction. So what this guy sees is that relative to him, is starting with zero acceleration, but it's starting, sorry, zero velocity, but it's starting with a relative acceleration of this much. Starting with this, okay, with respect to this observer. Okay, so this is the relative motion of the block in the Planck's frame. This is what this diagram is showing you. This is how it's starting at t equal to c. So is this clear now, Diti? Okay. So in this frame now, for them to lose contact, what has to happen? The block has to travel from here to here. So half at square will become the displacement. From that you'll get the time. The displacement should become L. So that's the first method of solving this. Okay, where you're doing the Newton's laws solving part in ground frame, and then you're using relative motion. Now there's also another method where you can do the Newton's law solving part only in the non-inertial frame. We'll look at that also. That will also give you the same result. Yeah, I'll scroll up with you. Okay, so let's see the free body diagrams again and make sure you understand that. Yeah, I'll come to that stage. Okay. So, Diti, are you clear with the accelerations? A1, A2, you understood how we got? I mean, the decelerations actually, but okay. So now we'll come back to the relative motion part. And finally, after getting the relative acceleration, we'll just use the kinematics equation that what is happening is that at t equal to 0, this block is starting from here with u equal to 0 and a relative, which we know. Okay. So after some time, with respect to this observer only, this block would have reached here. So we have to find how much time. So for that, this length has to become that a relative into half t square. Okay, so that time will be 2 times L upon a relative square root. Okay, so then you substitute this and all, you will get the answer. So the whole thing is inside the square root, of course. Okay, so no, it will not be. The thing is, now both are getting decelerated better because friction is causing deceleration for both of them. That is the thing you have to understand. Na? See, the plank is slipping with respect to the ground. So the ground immediately applies a friction backwards on it. Okay. But now with respect to the plank, what is happening? Na? This is slipping forward. So the plank will apply a backward friction on it. Na? Okay. So there is a forward friction on this plank, but this one dominates. So it decelerates. And this one decelerates because of this. So that's why A1 and A2 are both backwards. Yeah, so that is the thing which is tricky in this question. To figure out the directions of friction, that's the tricky part. Okay. Now, once you got that relative acceleration, here, next step we are just using kinematics. This E relative you got. Okay. Now just use the kinematics. U is 0, so displacement is half AT square. But in the relative frame, Yeah, Tej, you understood this, no? So just ये कितना आ जाएगा? This will come out to be 2 times square root of L divided by mu G, something like this. 2 you can take common outside. Anyway, I will also solve it by the pseudo force method, and you will understand that they are actually one and the same thing, whether you go for relative motion or pseudo force. So alternately, we can do like this, that the first free body diagram you continue the way it is, no change in that. That you are seeing in the ground frame, the Planck's free body diagram. Solve this with respect to inertial ground frame. Okay. So you can see that the two frictions acting on it will be like this and like this. So it will have, in the ground frame, it will have a deceleration backwards. You take as A2 or whatever, it doesn't matter. You take this as A2 because it had a velocity in the forward direction. So you will get your A2 as F2 minus F1 divided by capital M. This one, right? So you'll get your A2 as that mu G into 1 plus M by 2. We'll get this like this. Okay. Now what you do next is, when it comes to this thing, the block, that one's free body diagram you make in the frame of the Planck. Now your observer is sitting on the Planck. So he's in the non-inertial frame of the Planck. So the observer himself has this acceleration A2 backwards. He has this acceleration A2 backwards. So on the block, there'll first of all be a pseudo force forwards. Small m A2. This is your pseudo force. Like this. Okay. And of course, there will be friction. Backwards. Okay. So in this frame, let us say it has a relative acceleration like this. Okay, so this A relative, it is the acceleration of the block with respect to the Planck. Okay, or relative to the non-inertial frame of the Planck. So that thing we are calculating directly instead of finding A1 and A2 and then subtracting. We are calculating that directly. So in this frame only, what this observer sees is that A relative is equal to this pseudo force minus this friction divided by mass. This is the block. This is the Planck capital. Okay, so this is becoming Ma2 minus mu by 2 mg divided by m. So it is A2 minus mu by 2g. Okay. Now you substitute this here. And we'll get this as. So you see, you're directly getting this A relative term, which we had got by using kinematics. If you notice here, we got the same value of A relative. Now you're getting it by solving this one's FBD in that frame only. Okay. And now also you can see that in that frame, the initial velocity is 0. Because in the ground frame, they both had same velocity. No? So again, with respect to the guy standing on the plank, this guy's frame, initially at t equal to 0, its u relative is 0, it's starting from rest, but it has a a relative, which is this value. Okay. So it will reach here at some time t, which we can calculate. So L equal to half e relative t square, and from that you get the value, the same value. Okay. So Didi, hope both these methods are clear to you. Okay. This is FBD of the block in the Planck's non-inertial frame, and this is in ground frame. Okay, very good. So this one question is, a good way to learn a lot of things, and it's a good revision of various aspects like pseudo force, relative motion, friction, limiting friction, all these things. Okay. Now let's take the next question which I've got for doubts, which is question number 26. Okay. So after 31, we will do. I'm going backwards now, so I will do question number 26. Is the next one which I've received for friction chapter, that is. Okay. So in case you might not have noticed, 31st is the last question in the friction chapter of H.C. Verma. So we'll do 26 next. Just go through it. Okay, this is done, people. Let's go through question number 26 then next. Yeah, 26 is also a good question. Okay. What about this one, question 28? Anybody has a doubt in question 28? That's also a tricky question. Okay, I'll wait. Okay, good. We'll do question 28 also, then we'll come to 26. Okay, Tej, done with this? Okay. Let's move on to question 28. So we have this entire system of pulleys and block kind of thing. So number of pulleys. Just a moment. Okay, then this thread goes this. Okay, so this is more or less the system here. Now, the thing that makes this question complicated is that all the surfaces have friction. Okay, it's very easy to make a mistake with the normal contact force and therefore the friction. That's why I'm referring to this question here. Okay. So this surface is also rough, and this is capital M, this mass is small m, and this surface is also rough. This has a coefficient of friction mu1, and this has a coefficient of friction of mu2. Between the block and the ground, bigger block and the ground is mu2, and the system is released from rest. So we have to find their accelerations. Okay. So obviously what will happen is in this one will tend to move like this with some acceleration a, let's say, and in this one's frame this will tend to move downwards. So we'll write this as a AR. It's a relative acceleration. It is the relative acceleration of the block small m with respect to the wedge capital M. Okay, so the acceleration of small m with respect to capital M, that is this minus AR j cap, if you take x and y axis. Whereas the acceleration of capital M in ground frame is AI cap. So that is why the net acceleration of the block will be the sum of these two. So it will be AI cap minus A relative J cap. So in ground frame, it will look like that block is moving like this. That smaller block, now, after some time, the wedge reaches here and the block is here. So it's having a net acceleration which is in this sort of direction. This is the acceleration of the block in the ground frame. It is a vector sum of these two things. It's the vector sum of this AI cap and minus A relative J cap. So this is the net acceleration of that block. That's something important to understand. Okay. So this is basically coming from a concept like this, that if acceleration of A with respect to B is acceleration of A minus acceleration of B, then that means the acceleration of A in ground frame is the relative acceleration of A with respect to B plus the acceleration of B. So this thing only we have applied over here. Okay, so that's one thing. The other thing is you'll also understand from constraint relation from thread length conservation, you understand that A relative will be equal to 2A. Okay. Because if this thread length here is X now, and this thread length is Y, then you will see that 2X plus Y plus this fixed length D is equal to the total thread length constant. Okay. So 2 times delta X plus delta Y is 0. So d2y by dt square is minus 2 times d2x by dt square. So this constraint equation. So no, apparently, Krish, what is happening now? Let's assume that the smaller block is small in size, but it has comparative amount of mass. So its weight is creating enough problems. The friction is not able to balance. I agree with you that if we assume that small m is very light in comparison to capital M, which it looks like because it's much smaller in size. But imagine something like this, no? Like the capital M is a low density plastic block, no? And small m is like a high density metallic block. So it's possible that the weight of that metallic block is so much is causing the plastic to shift. Okay, so that's what we have to assume in the question anyway, no? Because otherwise the system would not move, right? So you can even find the condition for this. There must be some, like, if capital M is coefficient of friction mu1, mu2 is given, then there must be some minimum value of small m for which the system will start moving. If it is less than that, then the system will not move. So we can investigate that also later. But here we'll solve it assuming that the motion is occurring. Okay. So hope the constraint relation is clear to all of you. Okay. Now let's get into free body diagram. Now before we get into free body diagram, let's try to analyze the forces in this diagram itself. So you can see that there is a uniform tension acting everywhere through the thread. So be very certain how we are taking that tension everywhere, because that will count in the free body diagram. So there's tension like this. Okay. Then what is also happening is that the larger block is pushing the smaller block with some normal reaction here. And this is pushing it back with equal and opposite normal reaction. So there is the interactive force of normal reaction between these two. Okay. And this is sliding down. So obviously there is friction now between these two. So this is applying friction in this direction. This is applying friction in equal and opposite downward direction. So there is kinetic friction acting here between these two. Okay. So those are the interactive forces which we'll have to take into account. Apart from that, of course, there are weights and normal reaction with the ground and all that. So we consider those. Second step is we are applying the change. No? We are just saying that just apply delta, the change in this whole quantity, 2x plus y plus d is delta L. Now delta L is 0 because L is constant. Okay. Even delta D will be 0 because D is a fixed length. But delta X is there, delta Y is there. Okay. So you can even think of it like a dx, or you can differentiate this, or you can also write this that 2 times dx by dt plus dy by dt is 0. Just apply differentiation also, it's the same. Okay, very good. So now let's move on to the free body diagrams. So this is where the question is not difficult, but it induces mistakes. Okay, so pay close attention here. So the wedges free body diagram we will make in the ground frame, in the inertial ground frame. And remember, the pulley is attached to it. So whatever force is acting on the pulley, that also acts on the wedge. So in the inertial ground frame, now this one is having an acceleration A, which you already seen, because there is tension, tension, and again tension acting here. Three tensions. Okay. Then there is this normal reaction that this guy is applying, the block. Okay. Then there is a friction that this block is applying. So let's say that is F1, that will be mu1 n, because we have taken this coefficient of friction as mu1. This was mu1. Then what else? There is its own weight. So that is capital Mg. Okay. So the ground is applying some normal reaction, let's say N2. And finally, because it's slipping like this, the ground is applying a friction, let's say F2, which is mu2 N2. So these all forces are acting, and it looks very confusing in this diagram. So let's make a proper FBD of it, where we show all the forces with arrows from the point. Okay. So there is the horizontal tension is a net of 2T, the sum of these two. The vertical tension is a net of T downwards. So we're done with tensions. Then there is one friction acting like this, which is mu1 n1 or mu1 n, let's say. There's also friction acting like this on the ground, which is mu2 n2. Okay. Then there is, of course, this one's own weight, capital Mg. The normal reaction the ground is applying, which is n2, this one, and the normal reaction that the smaller block is applying on it, which is n. Okay. And under the action of all these forces, it has an acceleration p. So let's write the equations. The net horizontal force is 2t minus n minus f2 is equal to capital M. Okay. So 2t minus n minus mu2 n2 is equal to M. Is the first equation we have. Okay. And vertical forces should be balancing. So let's write that equation. N2 plus F1 is balancing capital Mg plus T. So N2 we should be getting as Mg plus T minus mu1 n. That's our second equation. Okay. So these two equations we are getting from here. Now similarly, write this down. Okay, and next make the FBD of the smaller block, small m, in the non-inertial frame of the wedge, capital M. Do that next. Okay. This was the FBD of the wedge in the ground frame. That was this. Okay, so note this down and make this free body diagram. You will get two more equations from that. And this is a bit of a monster question because there are 5 variables in this. 2 normal reactions, one tension, and 2 accelerations. Okay, A and A relative. And 5 equations are coming. 4 from free body diagram, 2 plus 2, and 1 constraint relation, which is the A relative is equal to 2 times A, which we've already got. So in fact, this is equation number 2 because our constraint relation was equation number 1. And this is equation number 3. Okay, so let's see the other two equations now. Yeah, I'll scroll up. Just give me a moment. And if you've written this down, start with the other two equations. Okay. So now you have to make the smaller blocks free body diagram in the frame of the wedge. Okay, done, Tej. Okay, finish. It's fine. Okay, good. So this part is done. Now let's come to the final free body diagram. So now let's look at the free body diagram of this one. So this block we are looking at in the frame of the wedge. This is a non-inertial frame. So this is traveling with that acceleration A towards the right. So first and foremost, there is pseudo force on this block. So that is what is actually pushing the block against the wedge. And that's why the wedge is reacting back by applying this normal reaction. And once there is this normal reaction, because it's sliding, there is friction here, which is mu1n, which we saw. Then of course there's the tension in the thread, and there is the block's own weight. Okay. And in this frame, remember, the block has a downward acceleration of AR. AR is the acceleration of the block small m relative to the wedge's frame, okay, which is the non-inertial. That one, okay. And also we have A relative is equal to 2A, which was our equation 1, constraint relation. So we'll make use of that also later. So now for the vertical and horizontal axis, let's write. So along the y-axis, we'll have mg minus f1 minus n, sorry, minus t. Excuse me, people. Yeah, minus t is m into A relative. Okay. So this will become mg minus mu1 n minus t is equal to m into 2a ho jayega when we substitute this. So this is our third equation, sorry, fourth equation. Okay, and along the x-axis, the forces should balance. So just m should be equal to m. That's a very simple equation. Fifth equation. So now this is my system of equations. Okay, the 5 equations and 5 unknowns. The 5 unknowns are E relative, A, tension, N, N1. These are the unknown quantities. Sorry, N and N2. The normal reaction of that one with the ground. So 5 unknowns, 5 equations. Now solving will not be so tough. It's just a matter of substituting things systematically. So let's put all our equations together now. So I'm just bringing these 2 equations from here. And we'll start the substitution process. Okay. So first of all, substitute N equal to MA in this equation. So this equation becomes mg minus mu1 MA minus T is equal to 2 MA. So we get mg minus T is equal to 2 plus mu1 MA. Okay. And then substitute N2 over here. So this equation becomes 2T minus N minus mu2 N2, which is capital Mg plus T minus mu1 N is capital M. And then again substitute this one over here. So this will become 2T minus small ma So now between this equation and this equation, we'll eliminate the tension. So from here, we can write the tension as mg minus 2 plus mu1 ma, or okay. So we will now substitute that over here. But before we do that, this equation, let's just tidy it up a bit. So we get 2 minus mu2 into tension, okay, is equal to capital M plus small m into 1 plus mu1 mu2 E plus mu2 mg. So I'm just leaving this for a moment to note this down up to here. Then we'll see the final substitution. So now just one variable has to be eliminated. So you have to just substitute the value of tension here. Okay, so let's finish the solving part. So I told you this is a bit of a monster question, but you systematically keep substituting the variables, it's fine. So substitute this tension on this side. So this will become 2 minus mu2 into this thing. Small m g minus 2 minus mu1 a. Okay. On the other side, we have capital M plus small m into 1 plus mu1 mu2 a plus mu2 capital M g. Okay. So we'll just separate out these terms a little bit. So Let's just make sure we get this correct. So 2 minus mu2 into tension, where tension is m into g minus 2 plus mu1a, okay? That is equal to this whole side, capital M plus small m into this. Okay. So we find here. Now we have to just open this bracket. This term is fine. And this term is also fine. So now we will get this as 4 okay, we'll get this. Okay, so finally let's keep the terms of A on one side and G on the other side. So we will get something like this. So A will come out to be something like this. Maybe let's check. Yeah, I believe that is the answer. So it takes time and patience to solve, especially because we are solving this parametrically. Okay, any other doubts in friction in HC Verma? Question 26 now. Okay, I'll tell you about 26 also. Yeah, these are advanced level questions, definitely. And see, even in an exam like the advanced, you will get the numerical values given of capital M, small m, mu1, mu2, all that. So your equations finally after substituting will not be such lengthy equations. concept will be same, but if you substitute capital M, small m, mu1, mu2, g, all these things with values, then you are solving equations which look easier to solve. Yeah, they do take time to solve. Okay, I'll give you some idea about the 26th question. You have done 24th and 25th, na, Diti? Because then there won't be difficulty while doing this. You've done 24th and 25th. Na? The questions are in series actually. Same type of diagram, but with an additional concept. So there's an additional concept here that if a charge Q, okay, like a charge particle having charge plus Q, in fact, is put in something called an electric field, which is pointing like this. Okay. So E is electric field. You will study this in 12th about electric field. It is something which is in newtons per coulomb. Okay, and Q is charge in coulombs. Okay. Then it experiences a force which is given by this relation. Is the charge of the particle multiplied by the electric field. Okay, so F is the electric force. So this is not part of this chapter actually. Okay, he just included a question from an additional concept which you will learn in electrostatics in 12th. So this is all part of your class 12th electrostatics chapter. So he's included that in this question number 26. So you have done question number 24 and 25 now, because the question are related. That's why I'm asking. Okay. So obviously what is happening in this now, that in addition to the mechanical forces which are applied on the system, there is also the complication of electrostatic force being there. Because of the presence of this electric field. Okay, so this system is the capital M, small m. Then I think there is friction between the two of them, but not between the ground, right? What is given? The floor is smooth, but there is friction coefficient mu over here. This surface has friction coefficient mu. And then we are pulling this block with a force F. But now in addition to all this, now what another thing which is happening is that both the blocks, I think, are having charge Q. Okay. Suppose electric field exists in space in the vertically upward direction. The upper block carries Q on its top surface. So the upper block has a charge plus Q fixed to it. The lower block does not. And there happens to be a uniform electric field upwards also like this. Then we have to find the acceleration of the two masses, maximum horizontal force so that they don't move and all that. Okay. So let's understand. So on this upper block now, in inertial frame only, on the upper block with the charge attached to it, there will be forces of its weight electrostatic force, which we can write like this, QE. Okay, so this is your electrostatic force. Because of this electric field. Okay. Normal reaction, the horizontal force with which I am pulling, which is creating tension in the thread. Okay, which is tendency to slip is in that direction, so there is kinetic friction equal to mu n acting like this, and let's say it is accelerating with A like this. So now the other one will have an equal and opposite acceleration because they are connected by a thread. Okay. So on this one, what all forces are acting? There is tension. Okay, don't need to worry about the vertical forces so much. So n prime, but this friction, the equal and opposite friction is there here like this. So this pair of frictions is there. Okay. And under the action of these forces, they should have the same magnitude of acceleration but in the opposite direction. So for the smaller block M, we have the equation F minus T minus mu n is equal to small m. Okay. And QE plus normal reaction is equal to small mg. Okay. So substitute this over here and we have F minus T minus mu mg minus QE is equal to m. Okay. And then for the capital M block, we have the equation T minus mu n is equal to capital M. So this is our third equation. So again, substitute this n over here. So this will give us T minus mu is equal to m. Okay. So now it's very simple to add these two accelerations. I mean these two equations, just sum them up. So your tension will cancel out. So F minus 2 times mu mg minus QE is equal to m plus m. So if they are slipping, the magnitude of the acceleration for each one will be this. That is if they slip. And you'll also see that if F is less than 2 mu into mg plus QE, then A will be 0 for both. Okay, and static friction will be acting. Oh, sorry. Static friction will be acting in such a way that F will be equal to T plus static friction and T will be equal to static friction. So F by 2, this much static friction acts. Okay, so hope the question is clear, Diti. Just go through the whole thing once and make sure it's clear. Okay. So again, the limiting condition is that this static friction is less than equal to mu n. So F by 2 should be less than equal to mu into mg minus q. So F should be less than equal to. This is for no slipping. Whereas if they are slipping, then yeah, I'll scroll up. See, these are the equations. No? You've written down you've understood the free body diagram stage. Friction is opposing slipping, so the direction of friction is clear. No? So now you have to just solve this. No? Solve the 4 equations which you've got from the free body diagrams. Actually 3 equations, because the vertical equation of the second one is not required. Okay, so solving this equation 1, 2 and 3, which we have done here. So substitute the value of normal reaction from equation 2 in equation 1. That is giving you this equation. And then this equation and this equation. Again, you are substituting normal reaction here. So you're getting this one in equation 3. Now you just add equation 2 plus equation 3. No, this is only equation 2. This is only equation 3. So add them, so tension gets eliminated, and that's how you find the acceleration. So when they are slipping, if they are slipping, this is going to be the acceleration. Okay, so this is done. Now let's come to that 14th question. So 14th question, you have basically a situation like this, that you have something that is sliding down a slope. Okay. And the coefficient of friction between the tires and the vehicle is mu. So if it's starting with a speed u like this and maximum brakes are applied, okay, so if hard brakes are applied, if you're in a situation of hard braking, so it means the wheels are slipping, they're skidding on the surface. So there'll be kinetic friction acting. So hard braking means that kinetic friction acts on the tires because they're skidding. Okay. So what will happen here is that if you look at the forces, and we assume that the friction is enough to make it decelerate, we will have Mn. Okay. And so the rate of deceleration is going to be g into mu cos theta minus sin theta. And you substitute these. So just put the values which are given and you'll get the rate of deceleration. Okay. Then you can see that having applied the hard brakes, if your vehicle is stopping after covering some displacement s, so your v square is equal to u square minus 2as. So 0 is equal to u square minus 2 times g into s. So from this you'll get the value of s. So understood, Nanditi? You have to just apply the kinematics equation now. Now just substitute the values of mu and all which are given. I think mu is given as 4/3, isn't it? And the angle of inclination is, what is it, 37 or 30 degrees or something like that. Achha, you have to find the incline. So is the reverse. Okay, what we have to do is you have to find theta so that for u equal to 36 kilometers per hour, which is 10 meters per second, s is equal to 5 meters. Okay, so substitute these values. Theta is unknown. Is the question clear, Diti? Yeah. Okay. Okay. So with this, we'll bring today's lecture to a finish. Okay. So now we're done with all doubts and questions. So next lecture, we will be starting with the chapter called Work, Power and Energy. So in this chapter, again, you can use H.C. Verma part 1 plus module for questions and solved examples. And you can use Resnick Halliday and or NCRT for theory reading. Okay. So this will again be a lengthy chapter. So we will be starting with the first part of this chapter with the concept of work and kinetic energy. So that will be Sunday's lecture, day after tomorrow. So you can read a little bit ahead about that and come. Okay. So that's it for today's session, people. Wish you all the best. Okay. You have some notion of work done from 9-10 that it is force into displacement in the direction of force. So from there only we will continue on Sunday. Okay. That's it for today, people. Wish you all the best.